Today we are going to look at the effective reactance in an AC circuit when you have inductor, capacitor and resistor connected in series with voltage source, AC source. Before we proceed, we are going to use phasor diagram to represent the direction of the voltage. This VR, that is the voltage that flow on the resistors, that's VR. And then we have VL that flow on the inductor, where here is VC on the capacitors. Now when you have this type of diagram, let's take the resultant in these directions. And then this what we call phase angle theta. And then the distance from here, distance between the VL and VC here will be VL minus VC, where this is Z, this is V Z, that is V total. Now let's now use Pythagoras theorem to explain the concept further. From this angle, V Z square is equal to VR square plus VL minus VC all square. Therefore, recall that from Ohm's law, V is equal to IR. But in terms of AC circuits, here I Z all in square, where I is the current flow in the circuit, Z is the effective reactant in the whole circuit, equal to IR, that's the resistance in the resistor, plus IXL minus IXC square. Now what's the common factor there? We have current is common, or open the bracket with that be I square Z square is equal to I square R square plus I square XL square minus I square XC square. Now current is common to both sides, therefore I square into Z square is equal to I square, open the bracket, we have R square plus XL square minus XC square. Therefore current go with this side. At the end of the day, we have Z square is equal to R square plus XL minus XC square. Now take the square root of both sides. You have Z now equal to root of R square plus XL minus XC square. That's the formula used to calculate total resistance in LCR circuits. Now from this angle, let's look at the phase angle of the phase angle. Now since from this diagram we have this hypotenuse opposite and this adjacent, let's consider the opposite and adjacent together. Therefore we have opposite and adjacent, that's tan theta. That's tan theta is equal to, what's the opposite there? We have VL minus VC over R, over VR, that over VR. Now substitute the value of VL and VC, and then you have tan theta now is equal to IXL minus IXC over IR. Current is common, that means current will go with this, and at the end of the day we have tan theta now is equal to XL minus XC over R. Therefore theta now is equal to tan inverse of XL minus XC all over R. That's the phase angle in the. Now assuming we have inductor and capacitor circuits, and then you want to calculate the effective reactance, also known as impedance, and also the phase angle. How are you going to achieve that? Therefore, you're also going to use phasor diagram. We have this. This VL, VC. Then that's VT. Then from this angle, VT square is equal to VL square plus VC square when you use Pythagorean theorem. Now from this angle, I Z square, that is V is IZ, I'm considering the whole circuit, is equal to IXL square plus IXC square. And then we have I square, Z square is equal to I square XL square plus I square XC square. Now therefore, the common factor is I. That's XL plus XC. I go with I. Hence you have Z square is equal to XL square plus XC square. Z now is equal to root XL square plus XC square. Now when you have inductor and capacitor, the effective reactant is square root of XL plus square root of XL square plus square of XC. The phase angle of this circuit can be deduced from this diagram, where we have this opposite and adjacent. Then we are going to use tan theta. That is tan theta equal to, what's the opposite? It's VL. That's VL over VC, where theta is the phase angle. Now substitute the value of, what's the VL? VL is IXL and VC is IXC. Therefore, tan theta now is equal to XL over XC. That is, I go with I, that is current. Now, tan theta now is equal to tan inverse of XL over XC. And then where XL is the inductive reactance and XC is capacitive reactant, where theta is the phase angle of the circuit. Resonant frequency in an AC circuit is the point where the XL is equal to XC. That is, inductive reactance is equal to the capacitive reactance. From there, you can deduce the equation. That is, XL equal to XC. This is inductive reactance, this is capacitive reactance. But recall that XL is equal to WL, where W equal to 2 pi FL. This is known as angular frequency. And then this frequency, this is inductor. Now, XC is equal to 1 over angular frequency C. That's it. C, which is equal to 1 over 2 pi FC. Now, equate the two equations. That's, we have 2 pi FL equal to 1 over 2 pi FC. At resonance, F is equal to F of naught. Therefore, anywhere you see F, put F of naught there. Then we have 2 pi F naught L equal to 1 over 2 pi F naught C. Make this equation over 1. Cross multiplications. And then we have 2 pi F naught L times 2 pi F naught C equal to 1. Therefore, 2 times 2, that will be 4 pi square F naught square L C is equal to 1. Now divide the coefficient of F naught to both sides. That is, F naught square is equal to 1 over 4 pi square LC. And then take the square root of both sides. That 1 over root 4 pi square LC. 4 is perfect square. Pi square is also a perfect square. And then they have F naught is equal to 1 over square root of 4 is 2. Square root of pi square is pi, root what? LC. And that's the equation used to calculate resonant frequency. You know what?